Listen closely to your kitchen. That low, constant hum in the background is the sound of a machine that has barely changed since before the light bulb. The first working vapor compression cooling machine was patented back in 1834 by an American from Massachusetts named Jacob Perkins. He built a device that could make ice on demand, giving birth to modern food safety and medicine storage. This diagram shows the same core loop Perkins designed, which your fridge still uses today. A mechanical pump takes a special chemical gas and squeezes it hard into a small space, making it hot. The heat bleeds out through coils on the back, condensing the gas into a liquid. Then the machine lets that liquid expand into a wider space, where it goes cold, pulling heat out of the air inside the box. Every cold environment you rely on runs on this exact 19th century mechanical loop. Grocery store freezer aisles, hospital vaccine cabinets, and your car's AC are all entirely dependent on a pump squeezing gas. That system is clever, but it carries a severe physical toll. The compressor relies on moving mechanical pistons that pump up and down thousands of times an hour for years. Bearings loosen, seals fatigue, and eventually the moving parts fail. The second flaw is invisible. The synthetic refrigerants sealed inside those pipes inevitably leak out at joints, during service, and especially when scrapped. This visualization shows the atmospheric impact of those leaks. Take R134A, a widely used modern refrigerant. 1 single pound of it hitting the atmosphere has the exact same global warming effect as roughly 1,430 pounds of standard carbon dioxide exhaust. Recognizing this math, the United States passed the AIM Act in 2020. The law mandates an 85% phase down of these chemical fluids within 15 years. Meanwhile, the leading replacement chemicals are either highly flammable, operate under extreme pressure, or break down into compounds that make regulators nervous. Society is legally forced to abandon the working fluid its entire infrastructure relies on, with no clean replacement ready to swap in. This ticking clock forced researchers to figure out how to cool the world without using gas at all. To find an alternative, physicists looked backward to an effect discovered in 1805. If you take a thick rubber band, stretch it fast, and press it to your lip, it feels warm. Let it relax, and it feels distinctly cool. Forcing the structure into order releases heat. Letting it collapse back into disorder absorbs heat. That trick was mostly useless until 1959. A metallurgist working at a U.S. Navy lab was trying to develop better materials for missile nose cones when he accidentally mixed nickel and titanium together. The resulting alloy, named Nitinol, behaved like nothing else. It remembered its original shape and snapped back to it under strain. But more importantly, when you deform nitinol, its internal crystal structure snaps into a tighter phase, causing it to heat up by tens of degrees. Release it, and it drops just as sharply, drinking heat out of everything around it. Nitinol is a rubber band with the strength of aerospace metal. It is a solid-state refrigerant you can hold in your hand, with no gas to leak. So if the government invented this super metal in 1959, why isn't it in your kitchen? Because for 50 years, the instinctive way engineers tried to build these machines was by pulling thin nitinol wires in tension. This cross-section shows metal under tension. Every pull slightly opens microscopic voids, widening them into microcracks. Because a refrigerator continuously runs tens of millions of cooling cycles over a decade, that relentless repetitive pulling caused early nitinol prototypes to shear apart in weeks. Despite perfect physics, elastic caloric cooling gained a reputation as a beautifully broken engineering concept. It could cool a small volume impressively, right up until the moment it tore in half. That is where a team at the University of Maryland, working with the Department of Energy, made a massive mechanical pivot. They realized the problem was the direction of the force, so they stopped pulling the metal and built a system that uses hydraulic force to compress bundles of nitinol tubes instead. Look back at the microscopic cross-section. When you apply compression instead of tension, the microscopic voids that would normally grow into fractures are clamped shut on every single cycle. As the driver squeezes the tubes, they heat up. A simple loop of plain, safe water carries that heat away. When released, the tubes snap cold, and the water loop pulls that cold back to your food. No chemical gas is required. Simply changing the direction of force, from stretching to squeezing, shattered a 50-year developmental wall and created a viable, durable, solid-state cooling machine. A traditional gas compressor must run continuously and requires a large mechanical loop to function. A solid-state Nitinol core, however, can be driven in discrete strokes and scaled down to the size of a deck of cards without changing the physics. That exact modularity solves massive architectural bottlenecks for modern infrastructure. Next-generation artificial intelligence data centers and electric vehicle battery packs generate concentrated, ferocious heat in very small spaces. Solid-state elements can be sited precisely where the heat actually is. There are also extreme acoustic advantages. In military submarines, vibrating compressors create an acoustic signature. Removing the pulsing mass of gas means silent operation, which in that environment is a matter of survival. Elastocaloric offers the United States a scalable platform to move heat efficiently, anywhere, without relying on chemical fluids that regulators are actively trying to ban. To move this technology from a laboratory to a retail appliance store, manufacturers must solve strict economic hurdles. Nitinol is expensive and requires highly precise melting in vacuum environments. A fraction of a percent of extra nickel ruins the temperature phase change. The system also relies on a hydraulic driver to squeeze those tubes. That driver is a new mechanical component with moving parts, meaning appliance manufacturers now have to conduct years of durability testing to prove it can survive a decade of kitchen use. Finally, vapor compression is a genuinely excellent machine. It has enjoyed a century and a half of relentless manufacturing optimization by massive industries. Beating it on a factory line at consumer volume is an enormous task. It will take time to reach your kitchen, but the path to silent, safe, gas-free cooling is finally clear, entirely because engineers realized they didn't need to discover new laws of physics. They just needed to squeeze the metal instead of pulling it.